Okay, hopefully my microphone works. So let us get started. So let me autofocus my camera. Okay, so we're going to go over some wave stuff. Then we'll go over the questions in the book. Okay, so within a vacuum, a property common to all electromagnetic waves. Okay, again, these are going to be the things that can move in space. Okay, so what they're all going to have in common is their velocity. All EM waves move at a known constant, okay? And that known constant will be the letter C. It's on the first page of the reference table, and that is 3 times 10 to the 8 meters per second. So for example, let me pull out my handy dandy reference table. Give me 1 second. It's a little bent, but that's okay. Oops. So on your reference table, right, you would see it right here, letter C, boom. Although it says the speed of light in a vacuum, understand that light is an electromagnetic wave. And if you're like, how does one know that? If you go to page 2, the electromagnetic spectrum, all of these things, including the visible light spectrum, are part of the electromagnetic spectrum, which means that all of these things listed here are electromagnetic waves, okay? So after that, we have the diagram shown represents 4 waves traveling in to the right in the same transmitting medium. What type of wave is represented? Well, first we go after solutions that don't make any sense. So elliptical and torsional, we don't teach. So it's either longitudinal or transverse. Longitudinal, we kind of think of those compressions and elongations. Transverse is very similar to what a sine or cosine curve looks like on a graph. Okay, so these kind of up and down peaks and valleys or crusts and troughs, those are characteristic of transverse waves. Okay. Number 3, which wave has the greatest frequency? So keep in mind, frequency just means who's happening the most often. Okay, so which wave is occurring most often in their cycle. Okay, so if we look at the diagram above, we're trying to find a wave or one of these waves that's going to happen most often. So we trace A and we see that there's only one wave there. We look at B. B has 1, 2, 3, 4, 5, 6, roughly about 6 cycles happening. Then C has 1, 2, and D has 1 and kind of a half. So we do see that wave B has the greatest frequency since we see the most amount of waves. Okay, so B has the most amount of waves. Okay. If we go back to number 4, which one of these waves has the greatest amplitude? So obviously amplitude is going to be this space from the right here is what we call the equilibrium position or the rest point of where the wave would be if it wasn't moving. So that will look like, the amplitude will look like the distance between that position and either a crest or a trough. Okay, so this is again known as a crest. This right here is known as a trough. Okay, the trough is just the valley. The crest is just the top of the wave. So again, amplitude will be the distance between the crest and the trough. So obviously, choice D, we see the largest amplitude or the largest height on those crests and troughs from the equilibrium point. Okay. Oh, I don't know why there's so many lines here. Hold on, let me erase these. Okay. All right. Number 5, which part of the longitudinal waveform represents a rarefaction? So a rarefaction only happens with longitudinal waves, which is what is seen here. And this is a very fancy way to say an elongation or expansion of the longitudinal wave. So when they get smushed together, we call that a compression. So A would be a compression. And then again, we're looking for a part that is elongated. So if we look from B to C, the lines are long. I mean, from one end of B to the other end of B, the lines are elongated. So that is known as a rarefaction. Number 6, which area of the longitudinal wave area best represents one wavelength of the wave shown. So if we look back at the diagram, we want one wavelength for the longitudinal wave. So C only has nothing to do with it. D only is the entire piece, and then A and B, that's only like one section of a wave. So a wavelength is when we go from adjacent pieces, or rather the same piece. So in this case, adjacent compressions in the cycle. And I'm sorry, I realized you're not able to see what I was writing. Or adjacent rarefactions. So if we look, the other choice is B and C. This makes no sense, so therefore it has to be A and B, right? A compression and a rarefaction. Okay. And then the last question, which type of wave is classified as longitudinal? So again, this is something that's going to need a medium to travel. So example, this type of wave cannot travel in space as there is no medium for it. So if we look at our answer choices, some of us would say, oh my gosh, how could it be radio wave, right? Radio is an electromagnetic wave. It's part of our beautiful handy dandy electromagnetic radiation diagram. We see the radio waves right here. So this is an EM wave. Same thing right here. This is also an EM wave. Water wave is kind of a little bit more complicated. So again, this doesn't fall under it. So sound is going to be our most commonly used example as a longitudinal wave. Number 8. As a longitudinal wave travels horizontally, the particles of the medium vibrate. Okay, so first of all, they're never going to be in a spiral, and they're never going to be in a circle. So it's either going to be up and down vertically or left and right horizontally. So if I were to draw a longitudinal wave as like a slinky, and perhaps you did this in lab, oops. So these are my stretched out pieces, and then I get really close, and then really stretched out again, and then really close. Where's my little marker here? If we were a particle kind of right here, and our wave was traveling to the right, we would actually see this particle move left and right, left and right. However, it's not going to move with the wave. It's just going to move in its fixed position, okay? Because the position or the motion of the particle will be parallel to the wave's direction. So motion of the particle is parallel to the wave's motion. Okay, and like I said, it is moving to the right, so therefore we do see the parallel, right? We see this is parallel and this is parallel. And another way to help us kind of remember this, that word longitudinal, oops, right? Longitudinal. I like to think that the L's, I did not mean to write a marker, the L's right here and here, they look like parallel lines. So longitudinal, the particles would have to move parallel, and that's what this symbol means, parallel to the wave's propagation or motion, okay? So therefore it is horizontally. Number 9, the diagram shown represents an undisturbed medium and a medium through which a disturbance is moving, which is represented by the area B. Oh, I'm sorry, which is represented by area B. Okay. So definitely cannot be an amplitude or reflection. And remember, a rarefaction will be an expansion or elongation. That's no good. So therefore, it is a compression, right? And we see all these things are very tightly and squeezed together. Number 10, if the displacement of the particles in a medium is parallel to the direction of travel of the wave, this wave is classified, right? So we think of the symbol for parallel, these two lines, And we have to think, well, what word looks like the parallel lines? Yes, the longitudinal wave will look like that because the L and the L, so therefore it is choice D. Electromagnetic and torsional don't even make sense, and transverse moves a different type of way, so longitudinal is the only one that makes sense. Number 11, which diagram best represents a periodic wave in uniform medium? So periodic means that it happens at a regular interval, okay? And it's very rhythmic, right? It doesn't look like the pattern is there. It's easily identifiable. So A is only a pulse, okay? So this is only a pulse, so that is not a wave. You want a wave. If you like a choice B, this looks pretty good. It's at a regular interval. I see 1, I see 2. C is at an irregular interval in terms of the kind of spacing between the waves. So this is no good, this is no good. And the same thing with choice D, the amplitudes are irregular. Okay, so therefore it is answer choice B. If a disturbance is parallel to the direction of travel of a wave, the wave is classified as, so again, we think of the word parallel. Hopefully you might not have just seen me go, oh yeah, maybe you did, I don't know, hold on. So we think of the symbol parallel, which is those lines, and we're trying to think of a word that looks like that, again, which is the longitudinal wave, right? L and L, okay? So again, parallel is longitudinal, the L's make the parallel sign. A single pulse, that just means a single vibration or disturbance. Transfers, okay, so standing wave makes no sense, wavelength makes no sense. Waves in general never transfer mass, ever. Okay, that is impossible. Waves or pulses can only ever transfer energy and momentum. Number 14. Which two wave representations in the diagram have the same amplitude? Okay, amplitude is just height from the origin. Okay, so we're trying to find those things. So if we look at this, A and B, right here, oops, here and here, B has a smaller amplitude. B and D also has a smaller amplitude. B and C also has a smaller amplitude. A and C, we see that they're at the same height. So therefore, they have the same amplitude. Okay. Number 15, which represents the wave with the largest amplitude. Again, we're looking this height from the origin. So B's would be right here. Let's see. C's would be right here. D's would be right here, and A's would be right here. So clearly we can see A has the largest distance between the wave itself and the origin. Okay. Number 16, as shown in the diagram, a transverse wave is moving along the rope. In which direction will segment X move as the wave passes through it? So here, you want to identify the direction of the wave, which for us, it's moving to the right. So then we want to look in the direction opposite the wave as motion, right? So we're at X and we're going to look to the left, right behind X. Well, I see a crest, so I know I'm going to move up, then I'm going to move down, then I'm going to move back up. So in this case, we're going to go up and then we're going to go down. So if you see a crest, you'll move up. If you see a trough, you'll move down. Okay? A characteristic common to sound waves and light waves is that they are, well, sound waves are the things that are longitudinal, so this cannot be true. Transverse, well, that's only for light waves. And only light waves can travel in a vacuum. They do not require medium. So all waves, again, to keep this most important part, that they'll always transfer energy and they'll never transfer mass, regardless if it's a light wave or a sound wave. Okay? Number 18, as a longitudinal wave passes through a medium, the particles of the medium move. Well, again, circles and ellipses make no sense. Perpendicular, nope, because remember, longitudinal, I see an L and an L, and that means parallel. So therefore, it is choice C. Okay. Number 19, the diagram shows two waves traveling in the same medium for the same length of time. The two waves have, all right, so if we look at them, so the most notable difference is their amplitudes. They have the same wavelengths, and they also have the same amount of cycles happening. So their amplitudes are the things that are different. Number 20, what is the angle between the direction of propagation of a transverse wave and the direction in which the amplitude of the wave is measured? So propagation just means travels or traveling, moving. I just want you to know that that's what that word means. So we use propagate or propagation. So a transverse wave is a little different. So a transverse wave is actually going to look like our sine and cosine. And that's kind of like a terrible drawing. So I'm going to redo that. So with this, our wave will propagate to the right. However, if I was a particle on this wave, I was here, I'm only going to be able to move up and down. And so if you think about it, the angle that gets made with the particle's ability is this 90-degree angle. And remember, the perpendicular symbol is the upside down T. So what helps us remember transverse from longitudinal is the following. If you write transverse with a capital T, and you take the T and you flip it upside down, well, then you're left with the perpendicular symbol, okay? So in this case, we're going to be 90 degrees. That's how we'll measure the amplitude of a transverse wave. 21, a periodic wave travels through a rope as shown in the diagram. As the wave travels, what is transferred between points A and B? So never mass and energy, never mass only, and it's never going to be neither mass or energy. It'll only ever be energy, okay? 22, the diagram given shows a transverse wave moving to the right along a rope. As the wave passes point X, the motion of X will be. So again, we know it's moving to the right. So we're going to look right past point X. So the first thing I see is a trough, so I'm going down. Then I know I'm coming back up because I see a crest. So I'm not going to be in a circle. I definitely cannot be left then right. That would be for a longitudinal wave, and that's not what we have here. And we don't have a crest first. We have a trough, so it'll be down, then up. The accompanying diagram shows a person shaking the end of a rope up and down, producing a disturbance that moves along the length of the rope. What type of wave is traveling in the rope? So again, these keywords is up and down. So remember, a longitudinal wave kind of will be left and right. Elliptical and torsional don't even make sense. So here we have a transverse wave. Remember, these are the ones that are going to look like sine or cosine curves on a graph. 24. The diagram below shows a tuning fork vibrating in air. The dots represent air molecules as sound waves move towards the right. Which best represents the direction of motion of these particles? So from this diagram, we see that some pieces are really close together and others are elongated, right? So this is a different way for them to represent a longitudinal wave. Okay, so first things first, two answers right away make no sense. A and B, those are terrible. But C and D could be like potential answers. So if we have a longitudinal wave, right, we see the double L's, we know that it has to be parallel to the wave's motion. So what that means is, if I was a particle here in space, I would have to move left and right because my wave is moving to the right, and that is how I'm going to get a parallel motion, okay? 25. As shown in the accompanying diagram, a transverse wave is moving with velocity v along a rope. In which direction will segment X move as the wave passes through it? So again, we know it's going to the right. So I look at point X, I look directly to behind point X to the left. I see a crest first, that means I'm going up. Then I see the trough, I'm going back down, and then I'm going to come back up. So it says, in which direction will segment X move? Definitely not just down, definitely not just up. It can't move down first because we see a crest. So choice C is no good. So it's up, then down, then up. Because again, when you see a crest, equals up. When you see a trough, that equals down. All right, base your answers to the following questions on the information diagram below. 3 waves A, B, and C travel 12 meters in 2 seconds through the same medium as shown in the diagram. What is the amplitude of wave C? So they did not give you an origin here. They just told you that the distance from the crest to a trough is 4 meters. So what you'd have to do is actually draw in an origin, right? So that means you're going to bisect it. This would be 0. So what that means is you're going to take this distance of 4 meters and you're going to divide by 2 because you're cutting it in half when we add the origin line. That means that the amplitude of A would be 2 meters. The amplitude of B is also 2 meters because notice how it goes from here to here. So then if we look at C, right, C is this wave right here. That's just one meter, okay? Because this would be 2, 1, 0, -1, -2. Again, when we put those minuses, it's not because we're saying that's a negative distance. We're just treating it like a graph, that's all. Okay, so the amplitude of C is going to be 1 meter. (27) A single vibratory disturbance moving through a medium is called a pulse. A node and an antinode are like not part of what you're learning currently, and a standing wave also makes no sense. 28. In an electric bell connected to a battery is sealed inside of a jar. What happens when the air is removed from the jar? So again, remember, an electric bell makes noises. It's like ding, 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 ding. And then we're slowly sucking the air out of that sealed jar. So remember, sound equals a longitudinal wave. And these waves require a medium. To travel. So if we remove the air, we are removing the medium. And if you remove the medium, well, guess what? There's no sound then. Okay, so that's like saying if we could go to space, take off our helmet, and we screamed as loud as we could, we wouldn't hear anything because there's no medium for our sound waves to travel in. Okay, so the bell's loudness decreases because sound waves cannot travel through a vacuum. Okay, so when you remove air from something, you are creating a vacuum. Okay. Which wave diagram has both wavelength and amplitude labeled correctly? So amplitude again is going to be the height. So amplitude, amplitude equals height from origin to crest / trough. It's either one or the other. A wavelength, which is the lambda symbol, is going to be one cycle of sine. And if you don't know what sine looks like, sine starts at the origin, has one crest, has one trough. That is one cycle of sine right there. Okay, so if we look at choice A, okay, I see pretty good job. However, the lambda is no good, or the wavelength. Okay, I look at B, the amplitude is terrible, and so is the wavelength. I look at C. Okay, the amplitude is good. The wavelength looks good. Let's make sure choice D is bad choice. The amplitude is terrible, but the wavelength is correct. So therefore, the only solution that makes sense is choice C. The diagram below represents two waves of equal amplitude and frequency passing or approaching point P as they move through the same medium. As the two waves pass each other, the medium at point P will. So these, again, are transverse waves. So transverse waves. And these waves will only move, oops, let me move my iPad, move up and down. So let's get rid of the ones that make no sense. Definitely not going to remain stationary. What the heck does it even mean to vibrate in and out of the page? That means it's coming towards us and away from us. That's crazy. Vibrate left and right. That's a longitudinal waves behavior. So they're going to vibrate up and down because they are transverse waves. If you're wondering how do I know that they're transverse, I simply look at the shape of them. I see this up, down, up, down, up, down. 31. The energy of a water wave is most closely related to its, so like a tsunami, right, is a very strong wave that comes and kind of smashes in a shoreline and like destroys areas and property. Well, the reason why it has so much power is because it's amplitude, right? It's height. So as it gets closer and closer to the shoreline, the wave starts to get bigger and bigger and bigger. So its amplitude increases, right? So here, think of a tsunami. Okay. Oops. Amplitude. Oops, let me just autofocus my camera. All right, there we go. Amplitude increases. So it gets stronger as it approaches the shoreline. Okay. 32, a tuning fork vibrating in air produces sound waves. These waves are best classified as, okay, so again, sound waves are longitudinal. Okay, again, longitudinal means we see the double L's, so they definitely cannot be transverse. And when we see the double L's, we have to think parallel. Okay, so longitudinal, good. Up, parallel, great. Let's make sure choice D is terrible. Longitudinal, perpendicular, no. So A, B, and D are terrible answers, and C is the only one that makes sense. Oops. 33. A transverse wave passes through a material medium from left to right, as shown in the diagram. Which diagram best represents the direction of vibration of the particles in the medium? So again, that word transverse. Just like we have our little trick with longitudinal, transverse, we take this T and we turn it upside down. That's the symbol that is used to represent perpendicular. Okay, so perpendicular means it can only move up and down, right? Because it has to be perpendicular to the wave's direction, and we see the 90-degree angle get made there. Okay, so therefore, it is answer choice C. Sorry, my computer kind of cropped out the other arrowhead. Okay. 34. Which pair of terms best describes light waves traveling from the sun to the earth? Okay, so light is part of the electromagnetic spectrum. So anything else that doesn't say EM is garbage. So C and D is no good because they do not use the description electromagnetic. Okay, let's think of this. From the sun to the earth, that means you're in space, aka a vacuum. Well, longitudinal waves require a medium to propagate. So longitudinal waves cannot move in space. That automatically eliminates choice B because that word longitudinal. So therefore, light waves are always electromagnetic and transverse. Okay, that's how they're described. 35. The energy of a sound wave is most closely related to its, okay, just like with the water wave, like if you ever had like a microphone and you're like screaming in the microphone, if you're able to look at like a meter, you're literally going to see your amplitude show up. Like you'd be really quiet, it's like really low, but then you get really loud and then you see the amplitude increase. Okay, so also the energy of a sound wave will be done via its amplitude as well. Okay, number 36. The diagram below represents a transverse wave. The distance between which 2 points identifies the amplitude of the wave. So again, amplitude is going to be the height from the origin to the crest, crest, or the trough. It's either one or the other. It's never going to be both, okay? So if we're looking at our answer choices, A and B is here. That makes no sense. A and C is from here to here. That also makes no sense. Okay, A and E, okay, that kind of makes sense. And then D and E. D and E is no good because that's the whole thing. That's from crest to trough. So that is no good. So therefore it is answer choice C. 37. Which type of wave requires a material medium through which to travel? Okay, it requires it. All right, so these are all examples. So EM waves do not require a medium because they can travel in space. So keep that in mind. Electromagnetic is like the overarching umbrella. So then I'm going to look like, okay, what are my other options here? Infrared and radio. Oh, that's crazy. Infrared is also an EM wave, meaning it also does not require a medium. Oh, what do you know? A radio wave is also electromagnetic energy spectrum. That means it also does not require a medium. Okay, because this is an EM wave. This is also an EM wave. Okay, so these guys, EM waves, do not need a medium. Okay, so B and D, therefore sound waves. Again, if we were to scream in space, no one's going to hear us. 38. The diagram below represents a periodic transverse wave, okay, traveling in a uniform medium. On the diagram above, draw a wave having a smaller amplitude and same wavelength as the given wave. Okay, so if they just want a smaller amplitude, we're just going to decrease the wave height. So I'm going to start here. Going to go down. Oops, I did not. Whoops. Let me redraw that. Okay, see how I have a smaller amplitude? All I've done is just change the height, but it has the same wavelength. So that means like where it touches the origin, that remains the same. Okay. 39. The diagram below represents a transverse wave traveling to the right through a medium. Point A represents a particle of the medium. Okay, right there. In which direction will particle A move in the next instant of time? So if we're looking at particle A, we're going to look right behind it. I see a trough. It's going down. Okay, so therefore it is answer choice B. Number 40. Oops. Let me get my piece of hair out of the way. The diagram below represents a transverse wave moving on a uniform rope with point A labeled as shown. On the diagram, mark an X on the point of the wave that is 180 degrees out of phase with point A. All right, so the first thing that I recommend doing is drawing in an origin. Boop, okay? A y-axis. Then I like to label my angles like you would, like if you're in Algebra 2. So here is 0. At the crest of a sine wave is 90. It reaches the origin at 180 degrees again. It hits a trough at 270. And it hits the origin again to complete its cycle at 360. Okay? And again, all I'm relating to this to is the sine function. You would like plug this into your calculator. You'll see the exact same picture pop up. Okay, so then I'm going to kind of guesstimate. I'm going to say that from here to here, where A is like 45 degrees, because it's like kind of bisected. It's like halfway from this crest to the origin. So I'm going to do 45 degrees plus 180 degrees. So I have 5. This is 12. So I'm looking for somewhere 225. That means I'm looking for a region in between here. So 225, it shouldn't be right next to 270. It should kind of be like kind of in the middle, kind of right here. So this is where my X would go. So from point A to point X, that's 180 degrees out of phase. Okay? And so like I said, if you break it up into these increments of these angles, 90, 180, 270, 360, it makes your life really, really easy. Number 41, which type of wave requires a material medium through which to travel? So if we look at all these, we might be very quick to jump to a radio wave because we assume radio is something that we hear. But then we look at this handy dandy reference table. And what do you know? Radio waves is an electromagnetic wave. That means it does not require a medium to propagate. So radio waves is out. A microwave. Oh, it's an EM wave. So that's definitely not true. Oh, wow, light. Oh, the visible light is part of the electromagnetic spectrum. So that's no good. So again, EM waves do not require a medium to travel. Okay, so they will be able to move through space. A mechanical wave, this is a type of wave that requires a medium to propagate. Number 42. A television remote is used to direct pulses of electromagnetic radiation to a receiver on a television. This communication from the remote control to the television illustrates that electromagnetic radiation. Okay, first of all, the type of electromagnetic radiation is actually infrared. Your iPhone actually has a filter on it. So if you were to like have your camera facing you and you like showed your like clicking buttons on the remote control, you'll actually, your phone has a filter and you'll actually see the red beam come out of the television remote. It's actually a pretty cool demo. Okay. So if we look at our solutions here, okay. If we look at what do you call it? If we look at, I'm losing having a brain fart here. If we look at our solutions, right? Is it a longitudinal wave? Absolutely not, because electromagnetic radiation is a, oops, where'd you guys go on my screen? Hold on one second. Let me just make sure that the YouTube is still going. Okay, cool. It's transverse wave. So this automatically, boop, possesses energy inversely proportional to its frequency. Has nothing to do with this. Diffracts and accelerates in air. It has nothing to do with that. This just shows that it is able to transfer energy without ever transferring mass. So we've literally sent a beam of infrared radiation from your remote control to the TV. It got absorbed. That energy got absorbed by the TV and got turned on. Okay. Number 43. The graph below represents the displacement of a particle in a medium over a period of time. The amplitude of the wave is. So all I do is go to my crest. I go across. I see it's at 4 centimeters. Okay, amplitude is height. So it's measured. It should be really measured in meters. But obviously in this case, the scale was in, wow, I love that. Scale was in centimeters. Sorry if I was writing and you couldn't see there for a second. Number 44. The diagram below represents a transverse wave propagating towards the left. A cork is floating on the water's surface at point P. In which direction will the cork move as the wave passes point P? So again, now we're going to the left, okay? So we're going to look right behind point P. I know I'm going to go down, and then I'm going to go up, and then I'm going to go back down, okay? Because I see a trough first, I go down, then my crest means I move up, and then I'm obviously going to come back down. So again, left and right is longitudinal. That's why these are terrible. You have a transverse wave, so you can only move up / down. Okay, so in this case, because we see the trough first, we know we're going to go down, then up, then down. 45. What is characteristic of both sound waves and electromagnetic waves? Well, they definitely do not both require a medium. Only sound waves need that. Electromagnetic waves can move through space. They're definitely not both mechanical waves, because again, mechanical means you require a medium, and sound waves are the only ones that require this and require this. Sound waves are also a type of longitudinal wave. So A, C, and D are terrible. Both of these waves, regardless of their abilities, are going to transfer energy nonetheless. Wow, I said 146. 46. The diagram below shows a periodic wave. Which 2 points in the wave are 180 degrees out of phase? Okay, so my recommendation, put in a y-axis, put in an origin, okay? And then I would definitely label my points. 0, 90, 180, 270, 360. Okay, so you want to make sure that whoever you are saying, you want to be 180 degrees apart. And each of these things go by a quarter of 360. Okay, so you're going to go by 90s. So A and C. So A and C are actually, A and C are from here to here is 180. So this works. But let's make sure the other answers are bad. B and E. So B is 90, 90. That's at 180 already. So we are at 270 degrees apart. So that's no good. Okay. F and G. F and G are actually 90 degrees apart. Okay, so again, these are no good. And D and H. So 90, right? 90, 90, 90, 90. That's actually 360 degrees apart. And so air, obviously, that is not good. Okay, so again, A and C, we see it's from 0 to 90, and then 90 to 180. That's 180 degrees apart for you. The diagram below shows a mechanical wave. A mechanical transverse wave traveling to the right in a medium. Point A represents a particle in the medium. Draw an arrow indicating at point A the initial direction that the particle will move in as the wave continues to travel to the right. So if it's traveling to the right, I'm going to look at A and I'm going to look right behind it. I do see a crest, so I know it's going to go up. Okay, so the crest tells me it's going up. Number 48, which 2 points on the wave shown in the diagram are in phase with each other? That means a 0 degrees phase difference. So they should overlap perfectly. Difference. Okay, so again, I'm really big onto drawing the y-axis and then kind of drawing the origin. It just helps me. I don't know, it's just easier for me to see that way. You don't have to, but I think it would be helpful. So basically, I'm going to trace one cycle of the sine curve. So this is one cycle. Then I'm going to trace the second cycle. Boop. So I'm going to take the letters from the first cycle and literally transcribe them over here onto the second wave. So A is going to go here. This is going to be B. And C would be over there. So the things that overlap perfectly are B and D. They are perfectly aligned. Okay, so what you need to recall is that one cycle of a wave is going to be one crest, one trough. That's one complete cycle. Once you identify that, then trace the second cycle and transpose what you see on the first wave onto the second wave, and then you'll just match up the points. 49. A transverse wave is moving towards the right in uniform medium. Which point X represents a particle in the uniform medium? Which diagram best represents the direction of motion of particle X at the instant shown? Okay, first of all, transverse waves only move up and down. So anything that's saying left and right is terrible. That's totally wrong. And so now that we're moving to the right, we're going to look at point X and we're going to look at the particle. We're going to look opposite the wave's motion behind the particle. We see a crest. So we know that it has to go up. So therefore, it's answer choice C. Number 50. When a wave travels through a medium, the wave transfers. Again, never transfers mass, ever. And it's never not going to transfer energy. Okay, so it's energy only. 51. The diagram below shows a transverse wave moving towards the right in a rope. At the instant shown, point P on the rope is moving towards the. We're going to the right, so we're going to look right over here, like right behind this. I see the start of a crest, so we're going to go up to the top of the page. All right, so there's some other questions. A wave with a frequency of 14 hertz has a wavelength of 3 meters. At what speed will this wavelength travel? So my frequency is 14 hertz. My wavelength lambda is 3 meters. My unknown is the wave speed, and the equation is v equals f times lambda. So I'm going to substitute. So I have 14 hertz times 3 meters. And if you use a handy dandy calculator, which I feel like I probably should know how to do this in my head, but it's okay. If I did 14 times 3, that is going to be 42 meters per second. Okay. Question 2. The speed of the wave is 65 meters per second. If the wavelength of the wave is 0.8 meters, what is the frequency? So now I have the speed 65 meters per second. The wavelength is 0.8 meters. The unknown is the frequency. We have v equals lambda times f. So I have 65 meters per second equals 0.8 meters times frequency. I divide by 0.8 on both sides. And my solution for the frequency is the following. 65 divided by 0.8 is going to be 81.25 hertz. Okay. A wave has a frequency of 46 hertz and a wavelength of 1.7 meters. What is the speed of this wave? So we have a frequency 46 hertz and a wavelength of 1.7 meters. Again, we're looking for the wave speed, so we're going to use the equation v equals lambda times f, or f times lambda. Again, the commutative property, order doesn't matter. So v is equal to 1.7 meters times 46 hertz. Okay. A wave traveling at 230 meters per second has a wavelength of 2.1 meters per second. What is the frequency? So again, the wave speed is 230 meters per second. The wavelength is 2.1 meters. The unknown is the frequency. So the only equation that you can use to help you solve is v equals f times lambda. So the substitution goes as follows. 230 meters per second equals the frequency times 2.1 meters. To get frequency isolated, you'll divide by 2.1 on both sides, 2.1. And your solution for your frequency will be the following. So 230 divided by 2.1 is 109.52 hertz. Okay. And then these questions are kind of practicing how frequency and period are related to one another. So if you recall, frequency is going to be 1 over period, and then you'll have period is 1 over frequency. However, these are not the only way to solve for them. If you recall, period is the time over number of cycles, whereas frequency is the number of cycles over time. So again, this kind of just shows their inverse relationship with one another. So this is the number of cycles a young girl is on a swing that completes 20 cycles in 25 seconds. What is its frequency and period? So the frequency, again, we're going to use right here is the number of cycles per time. So frequency is 20 cycles over 25 seconds. So this child's frequency, 20 divided by 25, will be 0.8 hertz. And the period, we'll just flip that, will be 25 seconds over 20 cycles. And that'll be 1.25 seconds. Remember, period is another way to say time. Number 2, A clock clicks 88 times in 22 seconds. Calculate the frequency in the period. Okay, so again, frequency will be 88 times over 22 seconds. So the frequency, 88 divided by 22. Oops, I did the multiplication by accident. It's going to be 4 hertz. And then the period will be 22 seconds over 88 times. So the period should be 1/4. So 22 divided by 88. And what you know, we get 0.25. So 0.25 seconds. Okay. Number 3. The time interval between flashes on a strobe is 1/80th of a second. What is the frequency of these flashes? So again, frequency is going to be the amount of time it takes per the amount, right? I mean, frequency is going to be the number of cycles per amount of time. So here they were sneaky and they gave us time. So remember, it's going to be 1 over period. So they gave me the period right here. So this is t. So it's 1/80th of a second. So all we're gonna do is plug in this 1 over 80. Okay. If you do that on the calculator, do keep change flip, you'll find out that the frequency is 80 hertz. And finally, a spring vibrates 24 times in 1 minute. What are the frequency and period? And the hint is that frequency must be in cycles per second. So 1 minute is 60 seconds. That was the only kind of red flag. So frequency, again, is the number of times per time. So 24,000 times over 60 seconds. And frequency is the following. So 24,000 divided by 60 is 400 hertz. And then the period is going to be 60 seconds over 24,000 times. So 60 divided by 24,000. And you get 0.0025 seconds. Okay. So now I'm going to go over those other questions in the book. Okay. Just give me 1 second. And let me find a pen. Okay, so these are the questions from the workbook. Let me just see if I can make my camera a little taller, but still make sure we could see. Okay, hopefully get my headphones out of the way. Yeah, here we go. So 31 says on the diagram, draw 1 or more arrows to indicate the direction of motion of point A in the next instant of time. Actually, let me just check really quick to make sure that these questions match up to the ones that were sent to me. Give me 1 second. Yep, perfect. So this is for the most part pretty much identical. All right, so we have a sound wave having a frequency of 40 hertz, travels to the right, and the medium is shown on the diagram. So I'm going to try to draw an identical diagram. So it says something that looks like 1, 2, 3. So A is right here. The wave motion is wave motion. Okay, and then they're saying from here to here is like 3 meters. Okay, so again, to kind of follow the rule that we've been using, we look right behind point A. I do see that I have a trough. A trough tells me it's going downwards. So I would put on point A, I would put a downwards arrow. Then it says on the diagram, label a point that is in phase with point A. So the first thing that I would do is kind of like, I'm going to redraw my diagram. So we have 1, 2. Okay, so I would draw in kind of like a origin kind of that allows you to bisect. So I know we always talk about sine being on like, oh, so it says a crest. This is just like negative sine. That's why you see the kind of inversion over the x-axis. So at point A, I'm right here, and I'm looking to be in phase. So in phase means perfect overlap or perfectly aligned. Okay. So if I were to kind of trace this wave, right, because I want a 0 degrees like phase difference. So this is like one cycle, then another cycle, then another cycle. I mean, we can very much start kind of like, I'm trying to think of the best way to explain this. Like I said, if this is one cycle, it's hitting in the middle. So then we need to start another cycle. So right here would be like another point that would be perfectly aligned. Because if I were to take A and like move it over here, right, I trace my pencil, and then I do another trace here. A would be right here. It's at the origin. This would be like our 180 degree mark here on the origin. So this would be at another 180 degree mark again just for that specific wave. Okay. 33, calculate the speed of the wave. Okay, so our speed. So if we have the speed, we're looking for V, and we have a frequency of 40 hertz. We also have a distance. So 1, 2. So we have a wavelength of 3 meters. Okay. And we are looking to find the speed of this wave. So this wavelength is, or this, I'm going to put this as a distance rather. So wavelength is going to be one section, all right? And it's saying from here to here. So if I trace 1, 2, I actually have 2 waves here. So 3 meters divided by 2, right? I see 2 waves. Our wavelength is going to be 1.5 meters. So we're going to use V equals F times lambda. So V is equal to 40 hertz times 1.5 meters. We're going to take our handy dandy calculator and we're going to figure that out. We end up getting 60 meters per second as our wave speed. In order for us to find the period, right, in 34, right, so this is, sorry, I should probably label this 31. This is 32, 33, 34. So in order for me to find the period, I know that the frequency was 40 hertz. Remember, period is going to be T equals 1 over F. So T is equal to 1 over 40 hertz. And therefore, period, by finding the decimal form, 1 divided by 40 is 0.025 seconds. Let's see. Base your answers to questions 35 and 36 on the information below. The elapsed time between successive crests of a transverse wave passing through a given point is point. Okay, so this is going to be 35. Okay, so time is equal to 0, or time, 0.80 seconds. Okay, determine the period of the wave. So remember, period, so period, capital T, is time over number of waves. So in this case, what they've given us is 0.080 seconds over one wave. So the period t, or capital T, is 0.080 seconds. Okay? Calculate the frequency of the wave. Okay, remember, frequency is just the inverse of period. So frequency is 1 over t. So that means frequency is 1 over 0.080 seconds. So we're going to take our handy dandy calculator. We're going to do 1 divided by 0.080. We're going to get 12.5 hertz. Okay. 37 through 39. The distance from one crest of a water wave to the next crest is 4 meters. One crest passes an observation point every 2.5 seconds. What is the speed of this wave? Okay, so 37. So let's write out what we know. So we know that the wavelength is 4 meters, and we know that the period is 2.5 seconds. So for every reoccurring crest, I'm seeing 2.5 seconds, and they want to know the wave speed. So we're going to use V equals lambda over T. Remember, this is just another way V equals D over T, or V equals F times lambda. Okay, remember, these are the other ways. Mechanics versus wave, so it's like a combination of both of them. Okay, then we're going to just plug it in. So V is equal to 4 meters divided by 2.5 seconds, and that is the following. 4 divided by 2.5 is 1.6 meters per second. Okay. Then 38 says, calculate the time required for the wave to travel 50 meters. So here we're still going to, we're going to use speed is 1.6 meters per second. We're also going to use the period is 2.5 seconds. But now we want to know what's the, I'm sorry. We're actually looking for period because the wavelength is now going to become 50 meters. So period is the thing we don't know. So we're going to do we're going to do V equals lambda over T. So 1.6 meters per second equals 50 meters over T. How do I get T off from the denominator? I multiply on both sides. So now I'm left with 1.6 T equals 50. I divide by 1.6, and T is equal to the following. 50 divided by 1.6 is 31.25. 31.25 seconds. Okay, remember, period is a time, has as the units of time. Okay, just another way for us to say time, but for waves. Okay. Then we have 39. It says calculate the total distance. So 39. So again, we're still going to use the same speed. So V is still 1.6 meters per second. Time is now 4 seconds, and they want to know the wavelength. So again, we're going to use V equals lambda over T. So 1.6 meters per second equals lambda over 4 seconds. We multiply 4 on both sides, and lambda equals the following. 6.4 meters. Okay. Okay. Let's go to 40. It says write an equation that correctly relates the speed v, wavelength lambda, and period t of a periodic wave. So remember, on our reference tables, we're only given this. This is for mechanics. And then we have v equals f times lambda, which is for waves. So for us to kind of relate these things, remember, frequency is 1 over t. So to combine them, we're say v equals lambda over period. Okay. Number 41. Oops, let me move my camera. What the heck? Okay. 41. A wave x meters long passes through a medium of y meters per second. Oh, excuse me, through a medium at y meters per second. The frequency of the wave could be expressed as, so it says x meters. So this is 41. X meters equals the wavelength, and y meters per second equals speed. And they want us to find the frequency. So the formula is V equals frequency times lambda. In order for me to get frequency isolated, I divide lambda on both sides. So I have y over x equals frequency. And this would be the units. Okay, so that would be answer choice 1. Then it says, what is the unit for amplitude of transverse waves? So amplitude equals height. So therefore we use the meter, which is just the letter M. Okay. Number 43. The diagram, well, let me just move the camera up a little bit. Let me autofocus it. Okay. The diagram below shows a periodic wave W traveling to the right in a uniform medium. On the grid below, sketch at least one cycle of the periodic wave having twice the amplitude and half the wavelength of wave W. Okay, so this is 43. I'm going to move my book. I'm going to see if I can kind of move my book a little bit so we could see my drawing. Okay, so I'm going to just kind of do my best to kind of freehand a graph because I don't want to write in my book. Amplitude, this will be 0, 1, 2, 3, 4, 5, 6. Okay. Oh, they're actually going. Okay, they're all going by 0.1, 0.2, 0.3, 0.4, 0.5. Okay. So 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. Okay. And there's some line right here. Wow, that was terrible. Some line here. And then it goes by 0, 0.5, 1, 1.5, 2. There's some lines going this way. Yeah, I'm just kind of freehanding this, so it's not going to be super terrible. It's not going to be super great. So the current amplitude of the first graph was 0.2. So graph 1 amplitude equals 0.2 meter. Okay. And the wavelength, if we trace, was 1 meter long. So graph 1 lambda equals 1 meter. So I want twice the amplitude, but half the wavelength. So 0.2 times 2 equals 0.4 meters. That's my new amplitude. And half the wavelength. So 1 meter divided by 2 equals 0.5 meter. Okay, so new lambda. So now it's actually time for me to graph this. My wave has to be finished at 0.5. So there's actually like these kind of sublines in here, right? So and again, I want the higher amplitude. So I'm going to start at 0.4. But again, my origin point, see, they were really sneaky. We think it always starts on this y-axis. They were sneaky and they added in this 0 line right here. So you got to start at 0.4 up here. Well, before we even get to that. So in the middle of this, right, the crest in the middle between these two lines, that's where your crest is going to be. Same thing, if you were in between these two lines, you go down to 0.4 over here, has to be in the middle. So then all I have to do is from 0, so 1, 2, 3, 4. I hit my points. I clearly see my wave goes from 0 to 0.5, which is the new wavelength, and the amplitude is 0.4. How did I know where to put those points? Well, I know that one cycle of sine is a crest and a trough. Okay, so one cycle of sine equals one crest and one trough. Okay, that's it. All right. Number 44. A sound wave is produced by a musical instrument for 0.4 seconds. 0.4 seconds. If the frequency of the wave is 340 hertz, so frequency is 370 hertz. How many complete waves are produced in that time period? Okay, so they want to know waves, or they want to know not so much the wavelength, but how many complete waves? Number of waves. Okay. So, all right. All right, so here we go. So we have, in order for us to find the number of waves, right? So we have frequency equals 1 over t, or you could do it the other way, whatever. You're actually going to multiply these. So this is actually going to be your number of waves. Okay. Yeah. So here we're going to take 370 hertz and we're going to multiply by 0.4 seconds. So 370 times 0.4 and you equals 148 waves. Okay. 45. If the frequency of a sound wave increases, okay, so if frequency increases, then wavelength has to decrease. Regardless of what type of wave they are inversely related. Okay. Number 46. Which phrase best describes the wavelength of a sound wave in air at STP? Let me try to move the book up a little bit and let me move my camera down a little bit. So it says inversely proportional to its amplitude and inversely proportional to wavelength. First of all, wavelength is independent of amplitude. That's the most important thing. Amplitude is its own thing. Okay, so they're independent. Independent means they do not affect each other. Okay, so that's first of all. So that means that choices 1 and 2, where it says inversely proportional, like that's wrong. So we have to look at the answers that say independent. Again, so wavelength is independent of amplitude, but wavelength is inversely related to frequency, right? Because I said as wavelength increases, frequency has to decrease. Okay, so that means that the answer we're looking for is choice 3, independent of its amplitude and inversely proportional to its frequency. And 47, a water wave travels a distance of 10 meters in 5 seconds, which can be determined from the information. Well, with this information, I could totally find lambda over t, which is the speed. That's one thing. And then I can also find the frequency because I know that frequency is 1 over period. So therefore, your answer choice that you'd be looking for is choice 3, speed and frequency of the wave. So I hope this helps. And if you have any questions, you're more than welcome to email me.